Hello, everyone. Again, my name is Farr, and today, on behalf of my colleagues at Georgia Tech on the Reveals project, I'd like to present my work on the thermal extraction of water ice using concentrated solar thermal technology in ice deposits within Regolith lunar simulants. So the big focus of this work is to develop technology for the use of ISRU on the moon with a specific focus on water deposits in these permanently shadowed regions. The method in which we hope to extract this is to implement concentrated solar thermal technology, which can be done by setting up an array of heliostat mirrors around the rims of a permanently shadowed region and redirecting the sunlight down into these ice deposits to sublimate it. And since NASA won't send me to the moon themselves, we have to experiment using simulated lunar conditions using our high flex solar simulator and custom built reaction chambers. Alongside this work, we're also going to be employing computational modeling, utilizing X-ray tomography to extract system optimization and help improve efficient extraction. So some of the challenges that we have to overcome when using concentrated solar thermal technology on the lunar surface is the fact that lunar soil is reflective to sunlight and a poor thermal conductor due to the porosity in a vacuum. The solution to this is been modeled previously, which is to use an indirect solar receiver. This would be embedded into the regolith, which would capture and redirect the solar energy. It would move down into the trapped ice. We can also use selective coatings to optimize for the solar absorption and re-emission. The other benefit the system has is it would allow us to clicker.
It looks like they lost the slides on Zoom. And so, okay, there we go. Now it's sharing on Zoom now. Thank you.
Yeah, like I said, this is the indirect solar receiver, which would be embedded into the lunar soil to redirect and transfer the heat into the ice deposits. The other benefit of the system, it was allow enhanced heat transfer down into the soil deeper than we could just radiating the top due to the thermally conductive walls. And as I mentioned, since it can't test on site, we can use our high flux solar simulator, which is shown here on the left, which is an array of xenon arc lamps that can emulate up to 5,000 times the power of the sun onto a 40 millimeter focal spot that would be beamed down directly into our experimental chamber. The experimental chamber is our concentrated lunar and rapid kinetics reactor, named after another solar powered extraterrestrial. This system consists of molecular ion vacuum pumps to achieve high to ultra high vacuum conditions, connected to a pulse tube cryo cooler for those cryogenic conditions we're looking for, as well as mass spectrometer to analyze the partial pressures of the system and to measure the sublimation rates. Looking a little closer, we can see that inside we have a packed bed with the indirect solar receiver embedded into the wet lunar simulant, which the ISR we're using for these experiments is a silicon carbide tube due to its thermal and mechanical properties. And the packed bed is also fitted with an array of T-type thermocouples to measure temperature gradient across. So the main focus we're doing for this experiment is testing a variety of initial conditions and factors and see how that impacts sublimation rates, as well as to model different conditions that we might expect on the lunar surface. This includes varying the water content in the packed bed, varying the irradiation levels we might expect. One of the things we're trying to test is the impact of a dry simulant layer that may be placed atop the ice-laden deposits, as well as testing with various different lunar simulants like LHS and LMS from Regolith Labs to see how the crystal morphology might affect the sublimation rates. So moving forward to some of the experimental procedures, here's a top-down view of our Clark reactor. We would start with initial cryo cooling and vacuum preparation to get down to the conditions we'd hope for. Then we would turn on our solar simulator to have the irradiation pass through our quartz viewport, striking through a 40 millimeter steel plate, and then hitting the silicon carbide indirect solar receiver. During the entire experiment, the pressure is analyzed using an ion filament gauge, as well as the partial pressure with a mass spectrometer, so we could see the water vapor and all other trace gases. During the experiment, any sublimated water vapor that comes off is captured at the outlet of the vacuum system using a desiccant trap, which we can then analyze after the fact to measure the total quantity of water involved and correlate that with the mass spectrometer to get temporal sublimation rates. Moving on to some of the preliminary results, here is the cryo cooler performance connected to an empty copper crucible, showing that we are able to get near temperatures nearing 100 Kelvin, which is analogous to what we'd expect in certain PSR regions. This process is also being sped up while we're using liquid nitrogen and some of the upcoming experiments to speed up that process. For a different experiment here, we can see we started out around 160, 170 Kelvin before the simulator was turned on the dashed lines, and we can see 120 Kelvin degree temperature rise in as short as 20 minutes, as well as a thermal gradient start to form across that packed bed as we'd expect due to the low thermal conductivity. There is some weird results at the beginning with the temperature, but that was just caused by the loose wire thermocouple placement in some of the initial experiments, but that has been corrected with rigid thermocouple placement. And as mentioned, we're also measuring the mass during these entire experiments. Here we could see that prior to the simulator turning on, the system was very isobaric. Before there was a sudden spike in sublimation and thus pressure in the system. The sudden pressure rise actually so fast that it exceeded the pressure thresholds of our mass spectrometer. Hence why we have the dashed blue lines, which are the interpolated mass partial or the water partial pressure during these experiments. But it is exciting to see how we have the direct correlation with the total pressure and sublimation adjoining the simulator activation. Outside of these experiments that we're running, we're also doing some computational modeling as we discussed. Here are some of the initial 2D axisymmetric meshes and modeling that we've done, where we could simulate 10 kilowatts or 10 suns worth of radiation for a total of 30 minutes. As you can see, the improvement that these indirect solar receiver has in conducting the heat down into the packed bed, much more than just irradiating the top. However, we wanted to move forward to some three-dimensional modeling. And so thanks to the help of Lawrence Berkeley National Labs and Dr. Elizabeth, we were able to incorporate X-ray tomography scans, which produce high-resolution MRI-like scans of the three-dimensional packed bed. We can then take this stack of 2D images and convert that into a 3D object using some in-house software, which we can then import into ANSYS to perform heat and mass transfer modeling at a higher fidelity than before. The other benefit to this 3D modeling using X-ray tomography is we can generate volume averaging correlations for things like the porosity or the diffusivity through the packed beds, which before wasn't possible. And so just to summarize, through this work, we've demonstrated how we can use concentrated solar thermal technology in conjunction with an indirect solar receiver and applications for lunar water extraction, showing some preliminary results with the feasibility of the experimental setup for this water extraction, as well as working to identify critical factors impacting lunar regolith sublimation. We're also hoping to advance ISRU through the innovative experimental and computational modeling and hope to establish the moon as a pivotal resource hub for future space missions, as shown by my artistic rendition of a lunar spaceport. And I'd like to thank the support of the Reveals team and Survey, as well as we continue this into the Clever project for the work and support. Thank you.
Okay, I think we have time for another question. Go ahead, Carl.
Hey, thanks. Yeah, ISRU is of particular interest to me. So you mentioned you had 5,000 kilowatts, but it doesn't look like you're running it at that energy. What power level were you doing this at? Because I noticed you got temperatures up to maybe 280 Kelvin, which is lower than I expect for
So yeah, the 5,000 kilowatts per meter squared actually melts through solid steel in a minute.
Exactly.
And a half. So we're not going that far. But for these experiments, I think the one we've shown that was around 30 kilowatts per meter squared, or 30 suns normal on Earth. But we can vary that with potentiometer anywhere down from 10 all the way up to, for one of the lamps, I think it goes up to 100.
Extraction of water from using solar illumination, people have looked at a lot. So keep looking at it, and the more you understand the diffusion of the desorbed water through the regolith, the more it'd be actually quite valuable. It's something that people have been. Aaron can probably speak to that as well. It's a challenge to drilling and everything else. So that's very interesting work. But also, what would be interesting is actually melting the regolith with the concentrated solar light. And one of the challenges we're going to have is landing pads on the surface of the moon. And currently, there really isn't a decided upon technology for the creation of those landing pads. If you can come up with a solar concentrator that can melt in situ a landing pad or create bricks or something like that.
Yeah, actually, that was funny enough, a pet project I tried to start recently during some downtime, which was trying to just take some of this lunar simulant, put it into the concentrated solar power or the solar simulator, and just see if we can use that to melt it. And not for the launch pad, this was to try to make the mirrors that we would use to redirect the sunlight. and make it sort of a, feedback loop on production. But that is something that I'm doing as a pet project.
Interesting. So I don't have requirements for Launchpad, but Starship's really heavy. Blue Moon's also quite heavy, so they're going to have to be pretty thick bricks, but it's something to consider.
Thank you.
Okay, thanks. Yeah, if you want to give a quick question.
I just had a quick question. So the question that I had was, I had three questions. One, how accurate are the simulations that you're doing in the lab to what actually is going to be implemented on the moon? Two, how much like regolith would you have to dig up and actually heat up to get a significant amount of water for like whatever they're going to use it on the moon? And three, what uses would the water actually have for like actual projects?
Yeah, great questions. The first one was how accurate we're modeling and running our simulations. We are trying to get down to temperatures in, below 100 Kelvin, negative, 280 degrees Celsius, or negative 180 degrees Celsius, negative 280, give me a surprise. And it's the same thing with the vacuum system. We're trying to get down to as high as the vacuum as can. Right now, we're at the ultra high vacuum state. But in the current system we have, we can't get any really higher than that due to the certain connections. But so those are the lunar conditions we're trying to run at. As for how much water we are trying to get out, depends on the certain models that we have and the efficiency of our system. Certain models estimated around 5% water at the higher end, 5% water mixed in with the lunar soil. And so, essentially you have 100 grams of lunar soil with 5% water, we can get 5 grams out of that. So it's, a lot they have to process. And as for what we can use it for, this work right here is, we can just get the water. We don't know what other materials are in there, what other chemical compositions. So I think it's safest to use it for synthesizing rocket fuel, which is why the tagline is using the sunlight and moon rocks to make rocket fuel. But that's my thoughts on that.
Okay, thank you.
All right. Well, thank you so much. Thank you.